Hi, my name is Daniel Penning, and I will present this talk together with Max Vincent Steck. For many years, I worked as a software engineer for safety-critical embedded systems. And during that time, I saw a lot of potential for better ways of doing testing. And for that reason, I founded MBEV, and we work on a new tool based on robot framework that makes testing low-level microcontroller code simple. The embedded domain is pretty reluctant to change. They have a lot of established tools. They need to navigate regulations. So it's not easy to get started with a new tool like ours. And that's the reason for this talk. We will explore if robot framework can be the bridge, the intermediate between an established test management tool and our actual test tool. What will we talk about? I will start by briefly introducing the challenge in embedded testing, and then show you the execution platform and how we use robot framework to enable embedded testing. I will also explain why we chose robot framework at all for a commercial tool. Then Max Vincent will take over, introduce the Testbench, and then explore if the Testbench can be the intermediate between robot framework and our test tool. So let's get started. What's the challenge in embedded testing? This system here might be in your dishwasher, for example. It's an embedded system that will need to monitor the water level, control the heating, control the valves, interact with the user buttons and the display. All this stuff is done by this embedded system. And there's a microcontroller on it to control it all. And this microcontroller will have pins. You don't see it because they are beneath the surface here, but they have pins and electrically communicate with all the stuff around. Unfortunately, if you have this system here, you cannot really system test it, because for system testing, the firmware, the software on the chip, expects that all the components that you need to connect, for example, the buttons, the display, the sensors, that they are physically present. And that's really difficult for testing because you usually don't have them on your bench. And system testing is individual for each product because each project will look totally different. So system testing is different. And that's why it's really time consuming. But nevertheless, system testing is state of the art in embedded testing. And we thought maybe we can, instead of focusing on the whole system, we can focus just on the microcontroller and its code. I mean, we write firmware, we write code for the microcontroller. The software developers are usually not involved in the PCB design. So they actually want to check only if the code is interacting with the pins correctly. And that's what our idea is about. We call it open loop testing, because we focus, like a unit test, we focus on a single component, on a software component, and ignore all the rest. We don't do simulations on the environment. So what's the key thing here that makes testing much simpler? We are more close to the software, and we have the same interfaces. If you look at the pins, they can be digital, they can be analog, there can be peripherals like CAN, UART, I2C, but still it's a range of peripherals, but they are always the same. Now there's a set of peripherals, and if a test system supports all these peripherals, then you can use a generic test system to check your code. And this is much simpler. And that's why we introduced the execution platform. It's such an open loop testing system. Basically, if a customer comes and say, I want to test my code, then we do this little PCB here, where the customer microcontroller, this is really specific to the project. We integrate this and make all the pins accessible. And this is inserted in the execution platform, and then you have a test system for your microcontroller code. And as I mentioned earlier, we use robot framework to access the device. So for that reason, we have two interfaces. The first is a code interface. To test actual code, the user needs to be able to flash a firmware, so put the software on the chip. For that, we have a robot framework keyword, should flash firmware. And then there's another keyword, get should invoke, that you can use to call functions running on the microcontroller. So we use robot framework to expose these keywords, and then you write your test on your host machine. Using these keywords, they run on the execution platform, and you can write your tests. Of course, you also need to have a way to communicate with the pins. And for that, we have endpoints. Let's say you want to test a CAN driver. Then you can configure an endpoint in our device on the specific pins. And the CAN endpoint will expose robot framework keywords, for example, to send a frame with specific data. And then our generic test system goes ahead and creates this frame physically on pins 19 and 20. And the same way you can, for example, create analog signals. That's something we will explore later in the example. For example, you can say that you want a specific voltage, 1.5 volt, on this pin 26. And then the test system will create this analog signal and put it on the pin. Okay. But the key thing here, all these functionality is exposed by robot framework to use by keywords. How does it look in practice? You always have a software, for example, with C and C++ code and a corresponding robot test file. So let's say your software wants to read an analog value. You can write a function, get analog value, starting the analog digital conversion, then waiting until the conversion is finished, get the value and return it. The stuff here is using some hardware abstraction layer from ST. It will communicate with the peripherals of the chip, reading this physical analog value, returning it. And you compile this, and then you use a robot test file. You can flash a firmware, example analog, that's the firmware here on the left side. And in your test, you can then, for example, set the static voltage here. It's the first step. This will use the analog endpoint. And then call another keyword .invoke to actually invoke this function here and read the result. And then you can do an assert on the result. This is open loop testing, basically a combination between using the code interface and the analog endpoints. Why did we use robot framework to access the device? First, there is a really large community. It's actively maintained. There are regular releases with a ton of new functionality. It has a great ecosystem, for example, good integration into Visual Studio Code. And what was really important for us in the beginning, it's easy to extend with libraries. For example, in the beginning, for prototype, we just used the remote library that's shipped with robot framework to provide our keywords. And you could get to results really quickly. And then if you take a look at the foundation, there are a ton of companies behind it, which ensures that it's just supported, that there are resources and it's maintained. So all these things led us to believe that robot framework is on a way to become somehow a standard. What we did not anticipate in the beginning when we chose it was that if you chose a standard, it's not limited to robot framework, but in general, relying on standards, you have positive cascade effects in the future. You can have them. So for example, Max Vincent will now explore if the Testbench can be used to create robot framework tests and use execution platform. And all this is only possible because both the Testbench and our tool use robot framework. You can connect different things together if you rely on standards. And now Max Vincent will take over and explore how this is all related and if indeed robot framework can be an intermediate.
Hello also from my side. I will now tell you a little bit about the Testbench and how the Testbench can be linked to the execution platform with the help of robot framework. The Testbench is a widely used, well-established test management tool A lot of companies already use it. A lot of people know how to use it. It offers a modular approach to building test cases. So you have test elements or test steps that you drag and drop to build test cases. If you have sequences of those test elements that you use over and over again, you can group them together to form macros, and then you can use those macros instead. When your project is getting more and more complex, it's likely that you have a lot of requirements to fulfill. So the Testbench offers to import requirements to the Testbench and link them to every test case you want to link them to. From there, you can get a good overview of which requirements have been met, which have been tested, which have been failed. Testbench also offers the possibility to export test cases as robot framework scripts and run them directly from the Testbench. After the successful execution of those test scripts, you can import the results back into the Testbench and have a detailed view on the results. So what would a test case for the execution platform look like in the Testbench? The test elements would correspond to the robot framework keywords used by the execution platform, and the endpoints and arguments are chosen as test parameters. So here you would have the robot keyword analog out 1 set static with the argument 1.5 volts. And in the test bench, you would have the test element set static with the first parameter to choose is the endpoint. So analog 1, 2, 3. And the second parameter would be the voltage, where you can just choose any value you want to. So here is a complete test case inside the test bench. And for example, in line 6, you can see the keyword set static with the first parameter analog out 1 and as a second parameter the voltage. And what would it look like to build a macro? So here, for example, you would have the two robot keywords set static and .invoke. And the first one, set static, you set a static voltage on a pin. And on the second one, you invoke the function on the dot, update the ADC value. And it's likely that those two test elements are combined very often. So you can group them into one test element or macro, which is then called set static and update ADC value, where you only have the two test parameters, the voltage and the endpoint. So this is the test case I showed you before. And this is how it would look with just using macros. So a lot shorter, a lot easier to understand. Yeah. So now I will show you how you can export, run, and import the robot framework tests. So here you just have the test cases, and from there you click on export, and you need to export it into a certain directory. And then you get a first idea of how successful the export was, if you have any warnings. So here everything looks fine. And from there, you only need to click on Run with Robot. And then the tests are executed, and you can now get a first idea if the tests are passed, if there was a fail. And then after this execution, then you need to manually import back the results. Those files are already chosen for you. And then here you get the confirmation again and just import it. And then on the right, you can see the metrics for the status of the tests. You can see that all 4 tests are passed. So here's a little comparison on how handwritten code would look like compared to Testbench generated code. And here, again, you can see the robot script, which is handwritten with the mbev keyword, analog out1 set static, and as an argument, the 1.5 volts. Compared to the robot script, to the Testbench generated script, where you can see Testbench uses resource files to generate the final executable robot script later for the execution platform. So now you can even take it a step further with fully automating the test execution with building a CICD pipeline. So this could look something like this. A change of code in the repository would trigger a build process. And this build process, then the outcome would be a compiled C or C++ program. And the build process not also triggers the export of the test case from the Testbench server via the REST API. So you don't even need to have the client running. It's possible to fully automate it with those API calls. And after the export of the test case, the robot framework scripts are generated and run automatically. And if those tests passed, you could then release a new version of your firmware or your software that has been tested. So here's a little example of what it would look like. For example, the code change in the repository would trigger this Python file. And here you can see, okay, which flags are set, where the log file is if anything goes wrong. And then inside the test bench, you could see a live update of what is happening. So here on the right, again, you see the metrics of the status of the test cases. So you have 4 planned test cases. And the moment you start the execution, or the execution is started automatically, then you can get live updates. So here you can see all 4 test cases are assigned. So everything what was planned is running or will be run eventually. And here at the moment, 2 are running. So if you wait a little bit, the first 2 finished and have passed, and now also the final 2 have passed. And after the run, you just get finished run in the command window and the execution was done. So yeah, to come to a conclusion, the main thing is that the Imbus Testbench generates and runs the robot framework scripts, and those scripts use the execution platform to perform those tests. So robot framework is a vital link between the established tool, the Imbus Testbench, to manage the tests, and the innovative solution by mbev to perform embedded tests. We are looking forward to the questions. Thank you for your attention.
Awesome. Thank you so much. All right, I just see Daniel in the green room. I don't see Max. So I'm just going to bring Daniel in. And wait, I see Max now. There we go. All right, guys, we're about to go live. Let's do it. Hey, welcome, guys, to RoboCon.
Hello. Hi, Joe. Hi, Joe. Thanks for having us.
Great to have you. Great session. Getting a lot of questions, so let's dive right in. Well, first one is Anonymous would like to know what libraries of Python packages are being used for embedded test automation.
Yeah, I think I can answer that one. So basically, we implement the libraries on ourselves. So we use the robot remote library to bring our framework to the end user, but we build up on it and implement all the keywords so that you can access all the periphery with specific keywords.
Cool. What are some of the reasons to use Testbench as a test management system? What are the next main benefits compared, for example, to like TestRail or Zephyr or X-Ray?
So maybe, yeah, I could answer this one. Actually, I don't know the other things presented here. I can only speak for Testbench, and because like I would say it's a very established tool, and yeah, it's often said that it's quite advanced in the tasks that it's doing. So that would be a reason to use Testbench. But I can't say anything about the other tools.
So just in my head, for some reason, when I think of embedded testing, I think a lot of C, a lot of C sharp. Who does the testing? Is it the developers, or do you have testers? Who handles that?
That's a good question. Could be both, actually.
All right, cool. Next question is, what are the blind spots in system level test automation and embedded system testing, and how have you taken the precaution about it?
Yeah. So that's a good question. I think there's a huge blind spot because in system testing you cannot access the internal states of the system. Think about the communication protocols at the pin level, like I2C, SPI. If there is some disturbance on these pins, you cannot really test it in system testing because you access everything from outside. And with this approach represented, you can just introduce all these communication errors like chain overflows and everything just at the pin level. So you can mitigate these blind spots. Of course, you need system testing as well, but these blind spots are very, very hard and expensive to address in system testing. So it's very easy at the pin level. So you, depending on the test case, you just need to choose the right test level to address it. I would say maybe Max Vincent has something to add.
Not to this one.
Nope. Okay. Peter wants to know the connection C code and robot firmware keywords was so simple as was shown on the, was it as simple as what was shown on the slide, or was there actually a lot of stuff under the covers going on to make that happen?
No, there is really only a little wrapper between. It's really easy. It's basically a one line to register all the functions so that you can use good invoke. It's really one line and a little bit of runtime package you need to compile, and that's it. So it's almost as simple as shown.
How did you deal with error flows in Robot Framework for your testing?
Well, I guess you have the standard output in a way, and need to look where the error comes from. So I don't know what to add to it. So
right. That's good. That's good. Gino wants to know, what challenges did you face implementing Robot Framework in the context of embedded systems, and how do you overcome them? I would think embedded systems has already standard tools, so why Robot Framework?
So Robot Framework is a great tool to address all kinds of tasks. But of course, for embedded, you just need access to, you need to implement these peripherals. And the challenge we really faced was the design of the keyboard. So we take huge amount of time to really think about what kind of keywords we need to provide to the user, so that it's both easy to use and still powerful enough so that you can address all your test cases. This really like, because all embedded systems are different, this is where we spend most of the time.
All right. Next question is, who will write the example analog.bin file? Is it in the build-in file?
Okay, yeah.
Max Vincent, if you want, go ahead.
Yeah, maybe this file like would be part of the firmware that you test, and this is something then which you include inside another main file that runs on the execution platform. So this is like a system file that is should basically be untouched when you test it. So.
And Renee says, info, if you're interested in knowing the difference between Testbench and other tools, ask me, but it's basically keyword driven and test data. So check out Renee in Gathertown for more info. Do you have capabilities to connect and do automation with Logic Analyzer? For example, Celia.
Yeah, we do. So Celia is really a great tool. We have a dedicated interface for it. So you can basically just plug it into the execution platform and have visualization of all your pins. And the automation thing, we are it's keeping up regularly. We are actually thinking about integrating it so that you can control CLI from your test and directly, basically, for example, configure CLI, start it from the robot test case, take screenshots, and integrate all this in your test report. Yeah. If you're interested in this, shoot me an email. The email was on the slide Maxim showed at the last moment, and then we can discuss it.
Very cool. And time for one last question. We have one last question. This is perfect. Can you mention the name of the software tool that can be used for system verification, and is it open source?
I don't know exactly what the
don't know anonymous.
means.
I think it was Robot Framework you were using, right, for most of the
yeah, Robot Framework and then Testbench. But it's like Testbench is not open source.
Gotcha.
Just okay.
Awesome. All right, guys, before we go, any parting words of wisdom you want to leave RoboCon? Daniel, we'll start with you.
Keep the community alive as it is. I think it's really great to see the progress in Robot Framework. The new features coming in and how responsive the developers are to feature requests. It's great to be part of it.
Love it. And Max?
Yeah, thanks for having us. I also had the pleasure to be in Helsinki like 3 weeks ago, and I really enjoyed like also participating in the community, just talking a lot. So thanks a lot.
Awesome. Great session. Thank you so much, guys. Really appreciate it. Thank you for contributing to RoboCon Online this year. Appreciate it. Cheers.
Thanks for having us. Bye-bye.
Awesome.